140 years ago, Voyager 2 departed Earth with equipment that continued to amaze scientists to this day. However, there is something too strange to overlook in the most recent discovery. It's possible that an AI-developed program discovered a secret message concealed in the pictures of this fabled spacecraft. Experts around the world have been astounded by the preliminary findings, which have sparked excitement and conjecture. Beyond the hazy pixels of Voyager 2's cosmic photographs, is there really something there? Or is this merely an error in the data? Voyager 2's launch and initial objectives. On August 20th, 1977, Voyager 2 launched on a Titan II-IE rocket from Cape Canaveral. It was half of the bold Grand Tour program run by NASA. Voyager 1, the second half, would take a somewhat different route. When mission planners realized that an unusual alignment of Jupiter, Saturn, Uranus, and Neptune would occur in the late 1970s, the idea for the Grand Tour was born in the 1960s. A spaceship with the right equipment may use this alignment to visit several targets in a single journey by taking use of gravity assistance at multiple large planets. NASA took advantage of the fact that such an alignment will not occur again for another 175 years. A variety of instruments were installed on Voyager 2 to provide information on planetary systems and the transitions between them. These included an imaging science subsystem with narrow and wide-angle cameras, a magnetometer, a cosmodetector, a plasma wave subsystem, and other support equipment for navigation and data gathering. Voyager 2 was initially scheduled to make visits to Jupiter and Saturn, with the possibility of an extension if the spacecraft continued to be healthy. Although it was not anticipated as a given in the initial mission plans, the craft actually proceeded to investigate Uranus and Neptune. Every device was constructed with sufficient redundancy and sturdy engineering to endure the harsh conditions of deep space, since dependability was crucial. The now famous Golden Record, a gold-plated copper disc with earthy sounds, pictures, and multilingual greetings, was also incorporated by the engineers. The record was largely symbolic, but it also demonstrated the mission's overarching objective of telling the tale of humanity to whatever intelligence might eventually intercept the probe. Heat from decaying plutonium-238 was transformed into electricity by radioisotope thermoelectric generators, RTGs, which powered the spaceship. Despite being steady, this power source would gradually dwindle over many years, necessitating careful resource management. During the first few months of Voyager 2, the spacecraft systems were tested, its instruments were calibrated, and its ability to traverse the hostile environment between Earth and Jupiter was confirmed. Mission crews started getting ready for the Jupiter encounter in 1978 after becoming sufficiently confident in Voyager 2's performance. Here, the craft would showcase its camera equipment, taking pictures of the planet's many fascinating moons and its whirling atmosphere. Saturn was located beyond Jupiter, and if all went according to plan, the vessel would continue on the grand tour of the outer planets to the lesser-known planets Uranus and Neptune. Voyager 2 captured breathtaking pictures of Jupiter's rainbow cloud bands and the famous Great Red Spot during its 1979 visit to the planet. The magnetometer examined Jupiter's massive magnetic field, which stretches millions of kilometers into space, while the plasma instruments measured Jovian space weather. Intense geological and perhaps subterranean processes were discovered during observations of Io, Europa, Ganymede, and Callisto. The discovery of active volcanism on Io in particular astounded experts. It was the first time explosions outside of Earth have been seen. With Jupiter in its rear, Voyager 2 accelerated towards Saturn by using the planet's gravitational pull. Its cameras picked up on minor ring divisions, braided rings, and enigmatic elements known as spokes within the rings when it arrived in 1981. In addition to providing information on how Saturn's environment interacts with the supersonic solar wind, the magnetometer traced the geometry of the planet's magnetosphere. Geological characteristics of Saturn's moons, such as Titan, Rhea, and others, were investigated. Despite having already visited Saturn, Voyager 2's equipment provided additional coverage and a second look at areas that the first probe had missed. The voyage of Voyager 2 became truly remarkable after that. The visits with Neptune 1989 and Uranus 1986. Surprises from Uranus, a planet with a significant axial tilt, included new rings that were faint but discernible and an oddly oriented magnetic field. Voyager 2 found several new moons, each with unique features. Models of the operation of huge planet magnetic fields are made more difficult by the obtaining that effect when bowl and shields are made more difficult by the magnetometer's discovery that Uranus's magnetosphere was tilted with respect to its rotational axis, with Voyager 2 taking pictures of the massive dark patch that resembled a storm similar to Jupiter's but was shorter in duration. Neptune proved to be just as exciting. The spacecraft made groundbreaking views of the moon Triton, where geysers spouted material despite the extreme cold, and discovered faint rings surrounding Neptune. After completing this extraordinary journey, Voyager 2 revolutionized planetary astronomy textbooks by demonstrating that gas giants were diverse, magnetically active, and surrounded by dynamic satellites. By 1989, Voyager 2 had beyond the known solar system and was widely regarded as the most successful planetary mission ever launched. Flight controllers steered Voyager too far into the outer solar system following the Neptune encounter. With that, NASA essentially terminated its main goal and shifted its attention to a longer-term mission to investigate the outer limits of the heliosphere. In order to strengthen the ship's capacity to provide energy to its magnetic cosmic ray and plasma equipment, the cameras that had captured famous images were put into standby or low-power modes. The reasoning was simple. There were no more large planets to photograph after Neptune, and it would be more efficient to use the power available to gather information on the environment that forms our star system's periphery. Operators had to cope with the RTGS's declining power. The spaceship had slightly less electricity each year to power its instruments, so they turned off heaters and other non-essential parts. The spacecraft continued to broadcast back a plethora of information on charged particles, magnetic fields, and plasma waves despite these limitations. The way interstellar radiation filtered into the areas that were still impacted by the sun's wind was detected by the cosmic ray detectors. Subtle changes in the solar magnetic field, which emanates from the sun, were detected by the magnetometer. By the turn of the century, researchers were paying more attention to how Voyager 2's data matched that of its twin, Voyager 1, which had left the ecliptic plane in a different direction. These probes' collaboration provided a nearly 360 degrees view of how solar wind combines with interstellar currents and flows outward. Researchers refined ideas on the shape of the heliosphere, whether it is spherical, comet-like, or susceptible to external pressure from the galaxy, by examining these readings over time. In order to explore how quickly solar eruptions moved and how they degraded over distance, the spacecraft tracked eruptions that traveled billions of kilometers. Voyager 2 was approaching the termination shock milestone, which marks the slowing of the solar wind from supersonic to subsonic velocity as it pushed outward. Researchers were interested in how cosmic rays might avoid the waning solar wind and how the local magnetic field would act. Predictions of cosmic radiation and space weather modeling benefited from such observations. Since signals took many hours to reach Earth, the data came slowly, but it was consistent enough to paint a larger picture of what lies beyond the intergalactic space. Entering the intergalactic realm. Following the passage of Voyager 1 in 2012, Voyager 2 became the second man-made object to enter interstellar space in November 2018. By keeping an eye out for sudden variations in cosmic ray intensity, magnetic field direction, and plasma density, teams on Earth were able to pinpoint the crossing point. Solar wind particles predominate inside the heliosphere and push outward. High-intensity cosmic ray densities increased beyond the heliopause, and the local magnetic field shifted away from the suns. Voyager 2's departure from the solar bubble was confirmed when these sets of signs converged at about the same moment, because it provided a second perspective on the intersection of the sun's impact and the galaxy as a whole. This move was crucial for astrophysics. The heliosphere can vary greatly at different locations along its boundary, according to a comparison of the datasets from Voyager 1 and Voyager 2. Due to changes in interstellar conditions or external pressure, some regions may be more compressed than others. Voyager 2 found some magnetic variations, for example, that were higher than predicted, indicating that the area where the outward flow ceases from our sun may change or pulse over time. The spacecraft was now in interstellar space, but its RTGS still contained enough energy to support a limited array of instruments, including the magnetometer, plasma detectors, cosmic ray subsystem, and sometimes the plasma wave subsystem. The problem of power distribution, turning off heaters, or rotating instrument usage persisted for engineers. Every time commands were issued or software upgrades were uploaded, careful planning was necessary because communication delays up 16 hours in one direction. Since the cameras were viewed as both a power burden and unlikely to capture useful images in the darkness beyond Neptune, they had been silent for decades at this point. The difficulty of taking pictures at great distances. It is difficult to take photographs in the solar system's farthest regions and beyond. At Jupiter, Saturn, Uranus, and Neptune, Voyager 2's cameras used to function well, but those planets had brilliant surfaces that reflected sunlight. The amount of solar illumination decreased to a fraction of what it is close to Earth by the time the spacecraft left Neptune's orbit. Built in the 1970s, the cameras themselves were not intended for astrophotography in extremely low light. To minimize cosmic ray interference and motion blur, significant ingenuity was required, even for brief exposures close to Neptune. It is significantly more challenging in interstellar space. Each watt counts, and the spacecraft's architecture only allotted specific wattages to each system. The RTGs lost power over time. In the event that the cameras were turned back on, heaters or other instruments might need to be turned off. There was also the topic of mechanical problems. The stepper motors, filter wheels, and camera shutters had been idle for a while. Unexpected issues could arise if these components jammed, potentially disrupting data storage procedures or harming electronics that were still required to operate for additional observations. Cosmic rays, which increase in frequency as the spacecraft departs from the shielding effect of the sun's magnetic field, was another role. Especially during extended exposures, these high-energy particles can produce streaks and bright spots on photos. An older camera may capture pictures that are dominated by random speckles if it lacks sophisticated shielding or error correction. Every cosmic ray strike complicates the already weak signals that could originate from the background by appearing as a flare in a single pixel or group of pixels. To get enough photons to stand out from the sensor noise floor, any photograph taken at these distances would require a prolonged exposure duration of many hours or longer. More cosmic ray strikes are invited with every extra minute of exposure. The resulting raw images may appear to be almost random static, even when there are several frames that can be stacked. By the early 1920s, there was a chance to recover genuine signals from severely distorted images thanks to emerging data processing techniques, including machine learning and quantum-aided denoising. Some engineers suggested restarting Voyager 2's cameras in an effort to get one last look at the heliop as a result of this technical change. Bringing the cameras back for one last try, a small team at NASA's Jet Propulsion Laboratory began developing a strategy in 2024 to revive the imaging science subsystem of Voyager 2, with the goal of detecting possible light patterns or emissions at the heliopause. They argued that if there are weak glows from plasma or dust processes, the vacuum of interstellar space may not be entirely dark. A few ultra-long exposures could provide a brief view of boundary structures if the camera and tape recorder worked properly and the spacecraft's attitude could be carefully controlled. The distribution of power was a significant obstacle to this concept. Any camera operation required shutting down or decreasing certain other devices because the spacecraft's overall power output was at an all-time low. This occasionally required hours-long partial shutdowns of research equipment or heating. The mechanical risk of relocating the shutters and filter wheels for the first time in decades was another problem. Each movement was meticulously tested by engineers, who used low-level commands to turn a filter wheel a little amount before waiting for telemetry to verify that everything worked. To make sure the lubricants weren't excessively viscous, they warmed the mechanisms. Because each phase needed a round-trip communication time of more than 32 hours, this systematic and sluggish technique took months. It was also necessary to update the software. More recent data compression techniques had to be combined with code from the 1970s. Flight engineers painstakingly incorporated blocks of new instructions to handle the camera exposures, even though the spacecraft's primary computers are basic by today's standards. This ensured that any mistake routines or watchdog timers wouldn't shut down the entire probe. Despite the expected high level of noise in the photos, tests revealed that the cameras were still capable of producing legitimate frame data. NASA authorized a brief imaging campaign with these preparations in place because they thought the possible discoveries regarding the heliopause may outweigh the expenses and dangers. The camera systems turned on, the shutters opened, the filter wheels turned, and the new commands were activated. In March 2025, for exposures that lasted 2 to 4 hours each, in order to free up the required watts, other instruments were put on minimal use while the spacecraft remained stable. Over the course of several days, each raw exposure was recorded on tape and then played back to Earth at extremely low bit rates. Although mission members acknowledged that the data would appear to be nearly pure noise, they thought sophisticated processing could reveal hidden signals, data analysis, and emerging hint. When the first raw frames reached Earth in April 2025, they largely looked like static brilliant spots from cosmic rays that occasionally streaked across the black background. However, researchers compared each image to magnetometer readings, plasma wave data, and time-stamped logs from the cosmic ray subsystem. For each multi-hour shot, they stacked the exposures, aligning them according to the spacecraft's known orientation and, when any stars were visible, their approximate positions. Real patterns were supposed to appear consistently, whereas random noise would change from frame to frame. A deep learning denoising model that was modified using Cassini ring imaging was employed by NASA. This model was trained to separate the random backgrounds that are common in that environment from faint ring or dust signals. The European Space Agency, meanwhile, used a quantum-assisted filtering pipeline that was invented for the analysis of very weak comet study data. To prevent bias, each team initially operated independently. After comparing the notes, they found that both pipelines consistently displayed filament-like formations that covered a sizable portion of the stacked photos. These filaments repeated in different exposures at overlapping time intervals, although they lacked brightness and clarity. Technical teams hypothesized that these filamentary streaks could be associated with cosmic ray or plasma wave data spikes. For example, the denoised images occasionally displayed a modest boost in certain filaments if the cosmic ray equipment detected a temporary rise in high-energy particles. For brief distances, it appeared as though invisible lines or tubes were illuminated by clusters of charged particles. Researchers compared each pixel cluster's brightness to the energetic particle flux that was observed in order to support this interpretation. Although not flawless, the association was sufficiently significant to exclude chance. Geometric abnormalities that resembled faint hexagonal cells or lattices were present in some frames. Experts debated if the spin synchronization of the camera was the origin of these formations. A straightforward mechanical explanation was not supported by the spin axis alignment tests, though. Others hypothesized that some plasma instabilities could appear as patterns resembling cells. Since so little had been visibly recorded at the heliopause, the general response was one of caution combined with interest. Although NASA did not commit to a single explanation regarding what the preliminary data suggested, The agency's partial statement in mid-2025 verified that the data suggested large-scale structures. Possible causes for filaments that are visible. As the controversy grew, researchers classified the filament's potential origins into a few primary groups. The idea that the lines shown in the stacked frames were magnetic filaments was one that was studied extensively. Zones of twisted field line may result from the local interstellar field becoming entangled with the magnetic field of the Sun as it extends outward in the solar wind. Low levels of light could be emitted or scattered by charged particles moving along these lines, particularly if they are accelerated by reconnection events that transform magnetic energy into particle motion. Dust emissions were mentioned as a second possibility. Dust grains traveling at interstellar speed may gather close to the helipole after colliding with cosmic rays or the solar wind. The dust may glow dimly as it charges. A prolonged exposure may show these filaments if the dust grains are grouped in sheets or threads. Solar wind flows may also carry material that bunches up at the boundary, giving them enough density to be slightly visible with careful denoising. A third theory focused on resonances and plasma waves. Wave instabilities at the border may result in localized sheets of increased particle density that could glow or reflect a small amount of sunlight, according to plasma physicists. If some modes propagate across the barrier, the wave patterns may appear filamentary. As an alternative, repeated lines or arcs could be formed by standing waves or resonant cavities in the helio sheath. This idea is supported by the correlation with cosmic ray flux spikes. More speculative people appeal to exotic physics, arguing that axi-like dark matter can change into photons in the presence of strong magnetic fields because wave activity can channel energetic particles in distinct channels. Some researchers have proposed this phenomena as a possible explanation for cosmic ray anomalies, although it has not been proved. Faint streams of light may be produced if dark matter encountered field interactions and was present in sufficient density surrounding the helipores. Although they acknowledged it was theoretically feasible, many mainstream scientists thought this was unlikely. Almost everyone thought that the recurring filament occurrences were interesting enough to merit further investigation, regardless of whether basic process was dominant. All of the suggested explanations left gaps while matching some aspects of the data. For example, magnetic filaments provide a better explanation for time correlation, even though dust glow can explain some brightness variations. Although a range of patterns could be created by plasma waves, the geometric shapes might not be made clear. For most, axion-like particles are still too speculative. This range of interpretations demonstrated how little is known for sure about the outer edge of the heliosphere. Beyond the filaments, there are spokes, hexagons, and other perplexing patterns. Both NASA and ESA observed what seemed to be hexagonal spokes or lattices. In certain frames, lines crossed at a 60 degrees angle to create a structure that resembled a 12-spoke cosmic wheel. Experts in plasma waves were intrigued by the quasi-periodic characteristic of the wave frequencies reported on Voyager 2, which could result in repeating or stable geometries over huge spatial scales. Should wave resonances be present, they might propel matter or charged particles into logical configurations that resemble the forms that emerge in fluid systems during specific oscillations. Others at NASA speculated that the spokes or hexagons might be partial sensor reading illusions. They checked for lens reflections, span axis alignments, and shutter timing discrepancies. However, it was less likely that they were just mechanical artifacts after multiple confirmations from different algorithms, one from NASA and one from ESA. There was no obvious explanation for a hexagon in the magnetometer results. As a warning, some pointed to the famous hexagon on Saturn's North Pole. Geometric patterns can occasionally be found in nature when fluids or gases are whirling. Perhaps a phenomenon that self-organizes into stable shapes is also supported by the helipore. The data on plasma waves and cosmic ray flux both increased in brief bursts that coincided with the spoke appearances, which is another intriguing viewpoint. This suggests a component that funnels energetic particles in a radial line on a periodic basis. Certain arcs or spokes may reflect density waves if the boundary region exhibits the behavior of a bell that rings in distinct modes. If they are real, the hexagons might indicate the areas where wavefronts converge. In the meanwhile, if the dust is divided into sections according to wave activity, creating a honeycomb-like pattern, dust-based explanations might still be valid. It would be premature to declare the presence of stable hexagonal cells or radial spokes as definitive, NASA said in a mid-2025 briefing. Random chance was implausible, though, because the manifestations were repeated in other frames and at different periods. NASA and ESA proceeded to analyze the data, publishing preliminary findings of possible dust or plasma interactions in peer-reviewed journals. University researchers from all over the world joined the conversation by using different image enhancement techniques or additional denoising methods. No one group came to a definitive decision. Proof that there is more to the puzzle than just one phenomenon. These results, along with the broader background and long-term research agenda, put Voyager 2 at the center of a new era in heliospheric research. Despite being a low-wattage, elderly spacecraft, it has provided an unexpected visual image of a domain that was previously thought to be invisible to conventional cameras. The importance goes beyond just taking beautiful photos. The interaction between solar plasma and interstellar matter may be shown by each subtle line or shape. Scientists can predict cosmic ray patterns, examine the system's form, and investigate how the sun's influence eventually gives way to galactic conditions by examining how magnetized plasma arranges itself at the border. Additionally, the data enhances cross-mission cooperation. The newly processed frames from Voyager 2 can be compared to observations from Earth-based radio telescopes or in situ measurements from New Horizons in the Kuiper Belt. The direct contact that Voyager 2 has with that area cannot be replicated by any of these viewpoints, but the correlation of several data streams can help to eliminate uncertainties. Together, ESA and NASA have a history of transforming data that seemed useless into discoveries, such as Cassini's ring science or Rosetta's comet investigations. Now they're applying those lessons to a probe from the 1970s that goes much beyond its initial purpose. When it comes to planning more camera exposures, engineers are still hesitant. The camera motors may seize or completely fail during mechanical activities, and each extra effort to collect data depletes valuable power from other equipment. It would be confirmed that the border region is dynamic and varies over short time periods if the additional exposures revealed variations in the spoke arrangement or the filament angles. If there were no changes, it could indicate that the pattern is more solid, which would raise additional issues about how or why it continues. In any case, every day Voyager 2 survives offers a chance to deepen our knowledge of how star systems interact with the larger galaxy. These signs of structure at the heliopause reflect more general astrophysical concerns, even from a cosmic perspective. Presumably, every star has a boundary zone where the interstellar medium meets its wind. Hexagons, spokes, or filaments may form around other stars if they can form around the Sun. Bow shocks surrounding some stars have been observed by observers traveling quickly through dense plasma or around star formation regions. Would a highly developed civilization be able to observe similarly ordered boundary features if it sent a probe to one of those stars? According to that theory, the distinctiveness of Voyager 2's data could be useful for interpreting interplanetary or perhaps galactic occurrences. These conversations often touch on the possibility of constructing a specialized interstellar mission. Designing a future probe may benefit from the lessons learned from reviving Voyager 2's camera for an imaging mission. Planners may outfit it with sophisticated software for real-time denoising, more resilient cosmic ray shielding, or contemporary sensors tuned for extreme low-light imaging. It could methodically map the boundary from many perspectives, obtaining high-resolution pictures of the ways in which dust, magnetism, and plasma waves form the star's last frontier in addition to particle flow data. If the patterns are found to be wave-driven or magnetically structured, they may also help to explain some of the anisotropies in cosmic ray flux observed in the vicinity of Earth from the perspective of cosmic ray science. Studying this effect could aid in space weather modeling or the development of improved debris shielding for upcoming unrefined missions to the Moon, Mars, if cosmic rays move via these filaments or spokes that could localize or alter their arrival patterns. By bridging the gap between solar physics, astrophysics, and interstellar medium investigations, these links demonstrate how even hazy views of the distant heliopause have a tangible connection to safer human exploration within the solar system. The prolonged mission of Voyager 2 continues to be an example of scientific cooperation. Knowledge from an old spacecraft preserved by meticulous engineering discipline led to a variety of possibilities, from dust luminescence to unusual dark matter interactions. The user community continues to improve the visuals, generating calls for more concrete proof and new sets of simulations. Although there is no universal agreement over the shapes or how they were created, the variety of viewpoints shows a strong, vibrant community attempting to address complex issues on the outskirts of our sun's sphere of influence. The main conclusion for the time being is that the heliopause is more than just a peaceful border. Ephemeral or not, the formations captured by Voyager 2's camera suggest powerful and continuous processes forming the furthest reaches of the solar winds. The information obtained already contradicts preconceived notions and encourages more efforts to visualize star-galaxy boundaries, even if the spacecraft is unable to capture additional images. The idea of using sophisticated data processing on older instruments has been proven by the collaboration between NASA, ESA, and several academic organizations. It implies that even a small signal extracted from nominal static can provide information about something that no human has seen firsthand. As a result, Voyager 2, which was launched during a time when slide rules and punch cards were used, is at the vanguard of exploring cosmic boundaries and establishing links spanning decades of advancements in science and technology. Thanks for watching another episode. Please like and subscribe for similar content.